Hello everyone. So today we are continuing working on our strengthening inequalities and valid inequalities that I believe we have started last time. Right. So last time we were discussing. We have discussed clique finding, right, and how we are building strengthening inequalities, and I believe that we have started introducing more more formal definitions and regular approaches towards defining valid inequalities. So what we are introducing all the time, so the strengthening inequalities and the clique finding, everything before it also was valid inequalities. And so let's formally introduce what valid inequality is. It's an inequality of the form pi x less than or equal than pi 0. That is it's a valid inequality for a set X if for all elements of the set this inequality holds. So basically, it's if you are thinking about X as a discrete or semi-discrete set that is defined by the type, like the best formulation P, then any inequality that cuts off. Let's say that this is our discrete or semi-discrete set, and we have a convex flow of it, and we have our other kind of formulation P, and the convex flow is let's say P star. Any kind of cut, any hyperplane that cuts off it can cut off some part of P, or it might not cut off any part of P. It's just a valid inequality, and everything on one side of it includes the set X itself, and therefore it includes the set P star. If this hyperplane is such that all of the elements of X belong to the set defined by the inequality, then we call it a valid inequality, right? The examples are, for example, let's say that we have a 5-dimensional space, and it's defined by a single inequality. An inequality x2 plus x4 greater than or equal than 1 is valid because x2 plus x4 equal to 0. But it follows from this fact that basically this inequality holds because the right hand side is greater than or equal than 0, and the left hand side is less than 0. This inequality is valid too. I believe we have discussed it earlier, but here you can just prove that if x2 is equal to 0, then x1 must be equal to 1, and therefore the following inequality holds, where left hand side is equal to 0 and the right hand side is less than 0. Actually, I'm not sure. We probably haven't discussed that in details, right? We have only discussed clique finding and the pre-solving. Basically, this IP pre-solving is a very much related thing to what we are discussing, to what I'm talking about right now. So basically, we are talking about logical expressions that formulate valid inequalities over the given that the variables in the inequalities that we are formulating are in fact binary. So we are constructing valid inequalities not for this linear inequality, but rather for the entire set, which is a discrete set. I feel like I should discuss in more details what exactly this inequalities here mean. Would you would you think that I should spend more details, or is it quite obvious why this inequality is? So like, can you? Okay, yeah, sounds good. So basically, what we are saying here is that um, so there are two variables, x2 and x4, that take part in this inequality, and if we assume that both like, so if we assume that this inequality does not hold, we can just show that if this inequality does not hold, then this inequality cannot hold either. Why is that? Well, if this inequality does not hold, it just means that both x2 and x4 are equal to 0, because we are talking about binary variables here. And if both x2 and x4 are equal to 0, then -2, which is on the right hand side of this inequality over here, and it has a greater than or equal sign, then -2 must be greater than or equal than 3x1 plus 2x3 plus x5. If it's possible to have this combination, but but on the right hand side of this inequality, we can see that all of the variables are non-negative, and therefore and they all come in with summation signs. So the right hand side of this thing is greater than or equal than 0, and the left hand side is less than or equal than 0, and we have an inequality -2 greater than or equal than 0, which is a false inequality, and therefore this thing can never happen, and therefore this thing can never happen if we assume that this inequality holds. And since this thing can never happen, then this inequality can never be violated by points from x. Okay, therefore x2 plus x4 is a greater than or equal than 1 is a valid inequality. Similarly, we can show that this inequality x1 minus less than or equal than x2 is valid. Similarly, we can assume that x1 and x2, x1 is equal to 1 and x2 is equal to 0. It's the only case when this inequality is violated. Like, let's assume that this inequality is violated, and then prove that if this inequality is violated, then the corresponding point does not belong to the set x. How to prove that? Well, we again put -2 on the left and on the left, and then we use the greater than or equal sign, because it's the contrary of the less than or equal that we have in the very beginning. We just switch the left hand side and the right hand side, and we substitute 1 instead of x1, and we substitute 0 instead of x2, and we get 3 plus 2x3 minus 3x4 plus x5 greater than or equal than, and then this thing is greater than or equal than 3, and this thing is like at least -3. So this thing on the right, it cannot be less than -3. Therefore, this entire expression cannot be is greater than or equal than 3 minus 3, which is equal to 0. And we again end up with the same inequality, that 0 is it should be basically we are saying that -2 is greater than 0, like greater than or equal than 0, which is a false inequality, and therefore this situation when x1 is equal to 1 and x2 is equal to 0 can never happen for any point of x, and therefore the original inequality is a valid inequality. Is it clear? Okay, let's take a look at a different example of the set x. So this set x has an inequality y less than or equal than some very, very large number times x, and also y is limited between 0 and 5, and x is a binary variable and y is not a binary variable. Then we can write down that y is less than or equal than 5x just because x actually for real only consists of points 0, 0, and also one y with the y being from 0 to 5. It just means that 0y is just never happens, because if x is equal to 0, then y also must be equal to 0. And this inequality is much tighter than this one, for example, and it can be replaced, and it would be a valid inequality that would cut off like a large proportion of the space. Let's take a look at another example. It's a very similar example, but now instead of binary variable, we have a non-negative integer variable x. And y is still a continuous variable. We have y less than or equal than some large number times x, and y is being limited between 0 and 14. We are saying that y less than or equal than 6 plus 4x is valid inequality. You can see it on the picture. Basically, this is the original inequalities. This is the y less than or equal than 10x, and this is inequality y less than or equal than 14. And this inequality that is dashed is in fact this one. So basically both of this, so I just have to say that both of this like approaches, so instead of having these two inequalities, you can just have this one, and it would basically give you a precise form of this constraint. And also it is going to be a valid inequality with no doubt. And I would not, so like, in order to prove that this is in fact a valid inequality, I would like to show you the more general statement that is saying that if you have this kind of two variable, or actually it can be extended to multiple variable case, where you have one integral variable and one real valued variable, with the situation that the real valued variable is less than or equal than some constant times the binary or the times the integral variable, and you have an inequality that is bounding the real value variable between 0 and, let's say, some upper bound b, then you can construct a valid inequality of this form, y less than or equal than b minus gamma k minus x, where k is a ceiling of this fraction b over c, and gamma is defined with b, c, and k that is defined above. Essentially, well, this is like a valid statement, but you can first of all, you can just you can check it basically by using the same logic as we had in this example over here. It just means that if like so basically you just need to distinguish cases when x is equal to 0 and x is not equal to 0, and then you will arrive at the solution of the at the proof of this more general statement. Let's take a look at the example of the application of this statement for more variables than just one. Let's say that we have a set X that is constructed with which is which is located in a 4-dimensional space, and it has the formulation P defined via a single inequality: 13x1 plus 20x2 plus 11x3 plus 6x4 greater than or equal than 72. So first of all, we have to say that so here we assume that x is greater than or equal than 0. I believe it's it should be plus here. So we can take this entire this entire inequality and divide it by 11 and round up the coefficients. What we're gonna end up with is 2x1 plus 2x2 plus 3 plus x3 plus x4 greater than or equal than the inequality where we have just divided by 11 without rounding up the coefficients, and that is by itself greater than or equal than the right hand side divided by 11. So we have this inequality here greater than or equal than this thing, which is a valid inequality just because we didn't do anything except for like rounding up the coefficients, which cannot decrease the value of the left hand side. And the smallest feasible value of the right hand side is 7. Just because we cannot really get a fractional number, and a value of 6 is not reachable, just because it would violate this inequality. Therefore, the left hand side actually its smallest feasible value is 7, and therefore the valid inequality for this set X is this inequality over here. Yep. That's a great question. It's an arbitrary number. I believe there was a question like this before. I think you asked it during the lecture. Probably a couple of lectures ago. You were asking if we were to divide by larger numbers, would we get better solutions? And it is in fact there are multiple values that you can divide it by. The thing that you would like to get is you would like to get fractional coefficients that you can potentially round up or round down. But this technique, generally speaking, so it's I think I started by saying that it's an example of this general statement. It's not an example of the general statement. It's an introduction of a new technique. So I would like to separate these two parts. I think the only example of this technique was when I was introducing it. There are more examples of this in the book, though, I think. Yeah, so let's switch to a more complicated example with mixed integer constraints. Let me first see. Okay, so I have that. Let me actually switch to a different slide deck. Here we go. Okay. Yeah, so let's take a look at how to use a similar approach of division in order to introduce additional inequalities, additional valid inequalities in a mixed integer rounding case. And so that we are talking about a new. So it's a different set X that consists of that is 5-dimensional now, and it's based on 4 integral variables and 1 real variable. The integral variables are X, and the real one is actually it's Y. And again, we have all of the integer variables being greater than or equal than 0, and we can again divide by 11 and round up the coefficients. Is it obvious that we can just round up the coefficients without creating a best constraint, like is it clear that we can actually round up constraints? It's not totally obvious. So you're when you are having this this inequality, so when you just divide by 11, let's say, you get this left hand side, right? And then x1, x2, x3, and x4 all have positive, like non-negative values. And therefore, if you multiply this now by some positive integer that is greater than 1, you will get like this number over here will become a greater number. And therefore, it will only, like, you will get something that is greater than or equal than this thing, right? And therefore, if you substitute, instead of this thing, you substitute 2, the sign greater than or equal is going to be a valid sign. You agree? And then I do it for all of the coefficients. So rounding up the coefficients is valid. And if you do that, if you divide by 11 and round up the coefficients, when you are dividing by 11, you would get this like this left hand side. Here I have already transferred y to the right hand side. The right hand side is going to be like this. So this inequality is equivalent to the original inequality. It's just divided by 11. And then when I round up the coefficients, I will get like this left hand side instead of the right hand side, which is a totally about it is a valid inequality, because whatever point x from the original set x I would substitute into this inequality would hold, right? Okay, let's say that we are looking for a valid inequality in this form, where we have like the first part of the left hand side is exactly the part that we have had over here, and then we assume that there is an alpha. We are looking for such alpha, so that we are getting so that this inequality, when we substitute that alpha, is going to be a valid inequality. Let us notice that in the original inequality over here, we had like if we grow y from 0 to 6, then the right hand side over here decreases from 6 and 6/11 to just 6. Therefore, if we get alpha greater than or equal than 1/6, then we would get an inequality of this form, greater than or equal than 7 minus alpha y, with at least as tight natural value threshold. So we are saying we are just saying that if y is between 0 and 6, the right hand side over here, when it's rounded up, is going to be equal to 7, right? And when our y becomes greater than 6, okay, let me actually plot it. Y, and this is going to be 72 minus y over 11. So y is going to grow from 0 to 6, and then it's gonna get greater values because it's bounded between 0 and something. So r here is also with a plus. Yeah. So as we grow y, this thing here goes from 6 and 6/11 over to 6. it goes like this, and the upper bound, it stays at 7. So the ceiling of this number stays at 7 all the time. So here, this thing here is 22 minus y over 11. And this thing here on the top is the ceiling of 72 minus y over 11. Okay, and then when we hit this point 6, this line continues to go down, and this line, dotted line, is actually drops and becomes this one. Do you agree with me? Okay, and so our aim essentially is to make sure that this dotted lines. So we would like to come up with a different inequality. We would like to come up with alpha, so that these dotted lines for the left hand side. So basically, we would need such alpha so that these dotted lines also repeat the ceiling for 7 minus alpha y, and also like over here and over here. So any alpha such that the ceiling for 7 minus alpha y coincides with the ceiling for this number would work for us. I would like it to be absolutely clear and like obvious why we need this. Oh, it's non-negative. It's not restricted from 0 to 6. I'm just, so it's defined everywhere. I'm just looking at it for now, just for values around 6, because at 6, the ceiling of the right hand side changes its value from 7 to 6. Doesn't make any sense, because I don't think it's well written in the book, so I would like to explain to you it right here right now. Yeah.
So basically, you want to make sure that this is
right. Okay. At least around 6, because as we go further, yeah, it's okay. Yeah. Exactly. Yeah, it's okay if it's greater, but it cannot be less. And basically, any alpha that is greater than or equal than 1 over 6 works for that purpose. And why so? Just because you can just check it that it works. And therefore the this thing over here is a valid inequality for the set X, just because if you take this part and put it to the right hand side, the left hand side is going to take like integral values only, and the right hand side is going to take values that are not smaller than the ceiling of this thing. Make sense? Cool. Okay. So basically, like there's like I called it a Farkas lemma. It's not like straightly a Farkas lemma, but it's very much related, and it can be proven from Farkas lemma. So basically, if you would like to know if an inequality is valid for a formulation, for a particular formulation, so it's a kind of it's an object in like it's a convex set. So if you would like to know if your formulation is if an inequality pi x less than or equal than pi 0 is valid for formulation P, you just need to check if there exists a non-negative vector such that the non-negative vector times the matrix A with which the formulation is defined greater than or equal than P, and U times the right-hand side of the formulation is less than or equal than pi 0. So basically, this inequality is valid for the formulation if and only if such vector U exists. So you can always provide with a proof that an inequality is a valid inequality by just presenting this this vector U. And now we need to make a single, like the most important kind of characteristic, or the most important observation that the further reasoning is going to be based around is the following proposition 8.3. That is saying that x is less than or equal than the flooring of B. This inequality is valid for this set x going into integer numbers such that x is less than or equal than B. Basically, this is something that we have already used. It's just now it's written as a proposition. And like a couple of an obvious example is, for example, x being equal to basically being formulated by formulation P in an n-dimensional space, with P given by this 7x, with P given by this four inequalities. For this four inequalities, we can sum them up with the constraints with weights U such that it's 2/7, 37, 63rds, and 0, and we will get the following expression. We know that x is greater than or equal than 0, and so 2x1 plus 0x2, we just basically we are flooring down the both of this coefficients is less than or equal than 121/21, and therefore it's just this inequality just results in saying that 2x1 is less or equal than the flooring of 121/21 is 5, and therefore x1 is less than or equal than flooring of 5/2, which is equal to 2. Therefore, you just got a so basically this inequality is something that you would get from this weights, and if you use a different set of weights, you would get even a tighter inequality, which is x1 less than or equal than 2. I just have to say that it is like an extremely powerful tool, and it roots from Farkas lemma, and it's quite common that you just it's not very useful to do by hand, because coming up with this coefficients is not a very simple task. But obviously, when you are doing simplex method or something like that, this is basically what you're coming up with. You're coming up with valid inequalities. This is the dual variables, right? The variables here are the dual variables. Okay, so this is basically a different approach towards constructing valid inequalities. Now let me spend some time explaining the total Gomory procedure, or CG procedure. Basically, it's it's based on the three main inequalities that can be used or constructed iteratively based on this observation with Farkas, connected to Farkas lemma. Let's say that we have an inequality a set X that is based on the formulation P, and it's integral in n-dimensional set. P is given to us with inequality AX less than or equal than B, and our matrix A consists of columns from A1 to AN. Basically, it's an M by N matrix, and U is a non-negative m-dimensional vector. The following inequalities are valid for P. First of all, if we just sum up the inequalities with weights U, we'll get valid inequality. If we sum up these inequalities with weights U and then floor the coefficients of xj, it's still gonna be a valid inequality for P. And then valid inequalities that are only valid for X are the inequalities where you floor both the coefficients of X and the right hand side of these inequalities. Is it clear why these three types of inequalities are valid? Is it like, can you tell if it's obvious to you? Can you raise your hand? It's absolutely obvious to you. It's not obvious. Let's come back to this example over here and see why in this example we basically have used it already. So here we have used the first inequality must be quite clear, just because summing up inequalities with the same sign and with the non-negative coefficients must result in a valid inequality, right? Now, regarding the second and the third inequalities, let's take a look at this example here. Here we basically have used the fact that here we have used the second inequality because we have floored this 2 and this 1 over 1/63. We have floored them both. And why is it true that it's a valid inequality? Well, first of all, x1 and x2 are both non-negative. And then if we take, for example, this this number, we have left-hand side already being smaller than the right-hand side, right? So it's we have the inequality less than or equal to. And if we substitute a smaller coefficient in front of x2, our left-hand side can only become smaller. Yep. The coefficient. I would say that they are all of them are non-negative. Yeah. Yeah, it's so B are non-negative. And so A are all non-negative, and B are like they don't have to be non-negative. And I think at some point above we were talking about having that without loss of generality, right? Yeah, I just forgot to remind you about that. But anyway, yeah, it was somewhere. Yeah, right here. Yeah, so basically, you normally would be able to consider your coefficients being non-negative. But I'm not sure. Yeah, I mean, that's true. Yeah, basically, so the left-hand side over here cannot be, so the left-hand side of this inequality cannot become greater if you reduce the coefficient, and therefore, wait, actually, now that I think about it, it doesn't really matter, because your flooring is always, you're always reducing the coefficient, right? Yeah. So it yeah. Yes. Yeah. Because actually this argument about having coefficients non-negative would not work here, because before we had binary numbers, and now we don't have binary numbers anymore. Therefore, it is important that we are not sign restricted. Thank you very much for asking that question. That's actually a good question. But yeah, here we need to understand that when we are flooring a negative number, we are getting a number that is larger in magnitude, but it's smaller in the absolute, like as a number, it's a smaller number. So basically, flooring the left-hand side will always get you flooring a coefficient on the left-hand side will always get you a smaller number. Therefore, the second inequality must be obvious, right? And then the third inequality is just saying that when you have floored all of the coefficients on the left-hand side, your left-hand side cannot be a non-integral number, and therefore you always will have to you always will have to have an integral number on the left-hand side, and therefore it doesn't really make any sense to bound an integral number by a non-integral number, and so you're just approximating the non-integral number on the right-hand side by the closest integral number. Does it make sense? Mm-hmm. Awesome. So now, like, basically, it's so what we have proved right now, what we have discussed right now, is that it's always true that like the these inequalities are valid for P, and this inequality is valid for X. And actually, so is it clear that if these inequalities are valid for P, then they are valid for X as well? Okay. So basically, all of these inequalities are valid for P, and moreover, there's a theorem, the theorem 8.1, that is saying that every valid inequality for X can be obtained through a sequence of this Chow-Gomory inequalities, like applied one after another in a sequence. Basically, it is saying that any valid inequality can be obtained by applying these three rules to the set of inequalities that you already have, which is kind of a nice thing. So basically, having this, coming back to this picture, when we had a set X, and we had the convex hole, the set called P star, and we have initial formulation for the set P. We can just apply these three rules in order to obtain first this facet of the convex formulation, then this facet, and this facet, and this facet, and this facet, and basically by applying these three simple rules, we can just bring a convex like we can get a convex hole of this set P star, and then just solve a linear programming problem over this P star, and we'll get a solution of the integer programming problem, which is quite fascinating by itself, right? Let us try to prove this theorem 8.1 see that we in fact will be able to get any inequality. Well, the proof is only for a binary case, but it's valid. Like this proof can also be extended to general case of any integer or actually any integer problem. So we have a formulation for a set X, and it's not an empty set. And the formulation is it has to be between basically it's bounded by all of the variables in the formulation are bounded by 1 and by 0, so it's within the binary cube, and we have a set of inequalities, additional set of inequalities AX less than or equal than B. Suppose that there is an inequality that is valid for X. It doesn't have to be like a facet of the convex hull. It's just some valid inequality pi X less than or equal than pi 0, and we are saying that it's valid for X with pi and pi 0 being integral numbers. Basically, we are saying that it's really not so basically going from it's sufficient to prove the statement for pi and pi 0 being integral numbers, just because you can if you have fractional numbers, you can multiply it by a very large number for it to become integral. If you have like some real if you have just fractional numbers, we can multiply the entire inequality to bring that to integral numbers. It's not a problem. So it's sufficient for us to just consider pi and pi 0 being integral. So this problem of let's consider a linear programming problem of maximization of pi X over the set P. It is a bounded P is a bounded set. Therefore, this problem must be bounded, and it will have some upper bound. Therefore, it will have to have the optimal value, which is finite. And let's say that T is the expression of a ceiling of the optimal value of this problem minus pi 0. Okay, so this is just we just defined a new value of T that depends on the optimal value of this problem. Any questions at this point? Yeah. So pi X, first of all, pi X is less than or equal than pi 0 plus T. This inequality must be valid for P for some positive value of T. For which positive value of T, it's basically this one. So it's simply a consequence of well, first of all, to begin with, it's since we assume that pi X less than or equal than pi 0 is a valid constraint for X, it doesn't have to be a valid constraint for P. Therefore, we have to have this T over here, right? We wouldn't be able to just say that it's valid for P itself. Is that something that I need to talk about a bit more?
Just to clarify, is pi X less than equal to pi 0 and AX?
So AX less than or equal to B A is a matrix, X is a vector, and then you multiply one by another, you get less than or equal than another vector B. This is A, this is X, this is B. And this system of inequalities is defining, so let's say that this is our lattice of integer values. And this thing here defines some like polyhedron P of this form, for example, that consists of like linear hyperplanes, and it only defines P, and the set X is the intersection of P with the set of integral vectors. So X is only this point that just happened to be inside P, right? Only the integral ones. So basically, X is contained within P, and so this is what we are talking like. This is what is related to AX less than or equal than B. Let's take a look at what happens with the pi X. So pi is in fact a vector. It's a row vector, and X is also a vector of the same size. So this is pi, and this is X, and this is less than or equal than a single number pi 0. And this thing right here only defines a single hyperplane, and this hyperplane is somewhere, for example, over here, and it's just a like you can think about it as another addition to this system of inequalities, which do not violate, which do not cut off any of the points from X. Therefore, it's called a valid inequality. So basically, this this inequality pi X less than or equal than pi, it can cut through the set P, but it cannot cut off the points from the set X. Therefore, it's called a valid inequality. Do you see the difference between X less than or equal than B and pi X less than or equal than pi 0? Yeah. Okay. Because if you don't, then I will explain once again. Okay. All good. Cool. So is it clear why we need T here? Okay. So basically, let me repeat once again. So if you do not add T, this pi X less than or equal than B than 0 might cut off some points from P. For example, this triangle here is cut off by this new inequality, and we need to push it a little bit up for it to not to cut off anything out of P. So we do that, and we have the exact. We actually know that this T exists just because this number here exists, and this number would be sufficient for like if we substitute this number into this inequality, we will get a valid inequality for P. Do you agree with me? Now we want to show that this inequality over here. So now we want to show that there is a value of M such that pi X less than or equal than pi 0 plus M times a summation over J's belonging to N0 xj plus the summation of times plus M times the summation of J's in N1 times 1 minus xj is valid for every partition N0 and N1. So it doesn't really matter how you partition your set of N variables. There is a value of M that does not depend on the partition. So you can just fix M, and then whatever you do with the partition, this inequality right here will be a valid inequality. We want to prove this. Yeah.
So there's a valid inequality for X or for
This is a valid inequality for P. Right. Because for X it would be obvious. Yeah. So we are trying to prove it for P, which is not obvious. Okay, so let's try to do that. If X is like if it's a number that is integral, then X. So like okay, let me explain it more here. So how are we gonna do this? How are we gonna show that an inequality is valid? And you will actually have to do it yourself in the homework and most probably in the exam too. In this particular case, we are looking at the points from the set P, This is the set for which we are trying to prove like validity of this inequality. We are looking at these points and we are checking that this inequality does not cut off those points. We start by checking points from P that are integral. If a point belongs to P and also it is integral, then it is it belongs to X2. If a point is integral and belongs to P, then it belongs to X. And therefore, since this part that like with M's, it actually is greater than or equal than 0 always. And we know that this inequality is valid for any point in X. Then we can just like the only thing that we can do is we can increase the right hand side, which is always good, gonna give us a valid inequality. Do you agree? Okay. If we assume that X is not an integral point, then there exists alpha greater than 0, such that the summation of j in n0 times xj plus the summation of j in n1 times 1 minus xj is greater than or equal than alpha for all partitions n0 and 1. How to know that this is the case? Well, we just take a value of the, basically okay, probably picture wouldn't help here. We are taking, so if X is not an integral vector, then there is a component, a single component that is not integer valued, and then we are picking a component that is not integer valued, such that it's closest to the actual such that it is closest to the corresponding integer value, and basically that that value is going to be alpha, because it doesn't really matter how exact. So both of these entries, like this entry and this entry, both of them are greater than or equal than 0. So it cannot, like the left hand side cannot be ever reduced. And then let's say that we have so this is let's say that our xj or x is the non-integral component of the vector x, and this is our lattice. So these values are integral, and there is, okay, let me actually modify this. So this is our lattice. This is some number k, and this is k plus 1. And we know that xi is between k and k plus 1, and let's say it's over here, very close to k, and then this value here can be taken as alpha, just because it doesn't really matter in which partition n0 or n1 it's going to be. In this summation, there always will be either alpha or 1 minus alpha. And since alpha is smaller than 1 minus alpha, the left-hand side is always going to be greater than or equal than alpha itself. And so we can take alpha as the smallest value over here. Yep.
So we're trying to prove that pi x is actually pi 0 plus m1. Trying to find a tighter value than the one above.
We are trying to find a tighter valid inequality than the one above. So our aim is, okay, let me show you what the aim is. The aim is to show that this inequality by x less or equal than by 0 is it's possible to construct this inequality from this set of inequalities by applying the CG procedure over here. Yeah, so this is the final aim. But now we would like to start with this inequality over here and show how we can construct a tighter inequality than this one using this CG procedure. And then we will argue that we are able to actually construct an iterative algorithm that is making a tighter and tighter and tighter bound using the CG procedure, eventually leading us to constructing this dimensional inequality. Yeah. So right now we are trying to prove that we can construct this original this new inequality by x less than 0 plus t using CG procedure. Okay. So yeah, I wanted to say that if x is not integral, then there exists alpha such that this thing over here, the left-hand side is greater than or equal than alpha for all partitions, and then we can just take m being greater than or equal or just equal to t over alpha. And if we do that, our statement over here on the top is true. So we like this inequality over here is in fact a valid inequality for some. We were able to find m such that it's a valid inequality. Do you agree with me? Cool. Okay, so now we are kind of gonna be constructing an induction. If pi x less than or equal than pi 0 plus tau plus 1 is a CG inequality for x, with tau being like an integral vector, an integral number that is non-negative, then so is pi x plus pi 0 plus tau plus this basically like this summation over the two partitions for essentially basically for any this is true for any partition. So we can just we can prove this statement by summing up the inequalities. First inequality is pi x less than or equal than pi 0 plus tau plus 1. This inequality is going to be summed up with the weight m minus 1 over m. And the second inequality is going to be pi x less than or equal than pi 0 plus this thing over here that we have already proven with weight 1 over m. So both of this inequalities are valid, and so their summation with different weights is going to be a valid inequality, and therefore if when we sum them up, it's going to be a valid inequality, and the summation of these two inequalities is going to give us this inequality. So basically we have just proven that if this thing is like holds, then this thing holds too for any partition. Now we are saying that if the following are CG inequalities, first inequality has some subset T0 of the coefficients, and then we are adding another probably not coefficient but component. So T0 is a subset. And that T0 is a subset of values from 1 to n, and P does not belong to T0. Yeah, and we also have another subset T1, and B also doesn't belong to T1 too. And if these two inequalities are valid inequalities, then by summing them up with coefficient 1/1/2, we can say that pi x less than or equal than pi 0 plus tau plus this like summation over like this two summations is also going to be a valid inequality, just because like summing them up with coefficient 1/2 is giving us this valid inequality. And now, like, why is this important is because of the next statement that we are trying to prove. By applying this for p equal to 1 to n minus 1 and so on 1, with all partitions t0 and t1 of numbers from 1 to p minus 1, we can show that if pi x less than or equal than pi 0 plus tau plus 1 is a CG inequality, then so is pi x less than or equal than pi 0 plus tau. Just because we can just remove components from this. We can write down this inequality over here, and then we can start removing components from this partition, one after the other, until we don't have any components anymore, and we will come to a conclusion that just pi x less than or equal than pi 0 plus tau is in fact a CG inequality as well, if this thing on top was a CG inequality, which defines an iterative procedure. And then starting with tau being equal to t minus 1, iterating for tau from t minus 1 to 0, this establishes that pi x less than or equal than pi 0 is a CG inequality. Basically, the only comment that we need to say here is that basically we are able to so like our initial inequality with this t, basically for some t, since it's a valid inequality for p, it can be constructed as a combination of inequalities from this set of inequalities, just by playing around with this with the coefficients u, just by this. Basically, it's just by this proposition over here. There exists u such that basically that certifies that pi x less than or equal pi x less than or equal than pi 0 is a valid inequality for the formulation p, and therefore this inequality over here can be constructed by just using the first method or the first trick in the CG procedure. And therefore like all of the other inequalities all the way to pi x less than or equal than pi 0 can be constructed using the CG procedure. Is that clear? You will not you'll not have to prove it during the exam, but it's important to know that CG procedure is in fact like basically it's a complete algorithm. You can show, you can theoretically you can solve the problem of integer programming, an integer programming problem, any integer programming problem, by just applying the CG procedure and then in the very end solving the LP relaxation, because any valid inequality can be obtained through a sequence of this steps. Okay, so let's switch to the topic of cutting planes. A cut is to define a cut, you need two things. First, you need a set x, and then you need a point x0 that does not belong to the set x. And a cut or a cutting plane is an inequality pi x less than or equal than pi 0, such that this inequality is valid for x. So basically, it's satisfied by any point in x, but it is violated by the point x0. So how to interpret it? In fact, for example, with the set x and its convex combination. For example, for this set x, there is a point that is x0 and it's outside of set x, and for that you can just draw a line, a hyperplane that would split, like it would satisfy all of the points in x would satisfy the corresponding inequality. Therefore, it would be a valid inequality for the set x. But for the point x0, it would be on the other side, and so it would be valid for x0. However, it's important to understand that there is also a point x0 over here, for which such cut just doesn't exist. We don't really care about those, because if a point is like this, it just means that it's inside the convex hole of the set x, and therefore we don't really care about cutting off points that are inside the convex hole, because convex hole is something that we are interested in anyways. So okay. So it's important to understand that there are points for which there are no cuts. Okay, so if we consider a mixed integer program, maximization of cx plus hy, x and y belonging to S, u and v in basically they're corresponding to the integral and real variables, and let P be the linear relaxation of S with the optimal value ZLP and optimal basic solution XLP, YLP, not in S. Not on the in the linear relaxation of this problem. Oh, sorry, not in the original set. For the problem at hand, the alternative to branching at this point. So basically, normally, if we were to just basically the only algorithm that we know of at this point that would be capable of solving a mixed integer programming problem would be a branch and bound algorithm, which basically would tell us that we are branching at this point. We just pick a point that does not have an integral value and then consider two cases, basically branching. An alternative to branching would be to find a cut, find a cutting plane for XLP and YLP, finding an inequality that violates this two, like that is a valid inequality for the original set S, but is violated for this XLP YLP point, and add this cut to the original problem, to the original problem formulation, to this set of inequalities, and we are done. And most importantly, cutting planes are guaranteed to exist if XLP and YLP are is a basic solution. So if we have basically what it means, that if like what is mean to be a basic solution, it just means that your point is a vertex of a polytope, right? And if it's a vertex of the polytope, then you always are it's like, and it's not inside a convex, like if it's a vertex of a polytope and it's still not in X, it just means that it cannot be inside the convex hull of the set X. That's what it means. Therefore, there always is a cutting plane. It might be not easy to find it, but that's fine. So the cutting plane method is the following. So the cutting plane method is a way of solution of an IP. Let P be a formulation of X and F be a set of addition about inequalities for X. It could be exponential, it could be finite, it could also be like an infinite cardinality. It could be just all of the valid inequalities. The smaller the set, like realistically, normally the set is not infinite. It's just a finite set. But it's still quite difficult to search over it. Let's say that this X tilde is the argmax. Basically the solution of the linear programming relaxation of the original problem. If X tilde is in X, then you just return X. That's it. If exists a cut, like if it exists one or several cuts, pi 0 inside the set of like the set of cuts that we are considering, the set of valid inequalities that we are considering. For X tilde, separating it from X, then we add violated cuts to P and go to step 1. Then we just add the violated cuts to the original formulation and return to solution of the LP relaxation. If no such cuts exist, then we apply branching. Now the question is, why don't we just put all of the like if F consists of inequalities, why don't we just add all of these inequalities to P and just solve it, the corresponding LP? Like that would be totally like reasonable thing. Why do we need to iteratively add cuts or valid inequalities from F to P and then resolve over time? Yeah. If you apply all of them, yeah, it would like since it's an exponential number of them, most probably there are so like there's so much of them, so that it's impossible to solve the this problem in a reasonable time, even though it's an LP. So it's not. It's like it would make the first step, even the first step, an impossible step to solve. So even solution of an LP with all of this additional inequalities would not be possible. I remember that when we were discussing TSP and okay, let me actually pull that up. Just one sec. Over here. Okay. Yeah, so when we were discussing the traveling salesman problem, if you remember, we have considered two kind of ways to solve it, and the first way was using the open source software, and the second case was to use the software by Gomory. And the first, like the open source software, we only solved the problem, the TSP problem, for 6 variables, I think, and then for like with 6 nodes, and for like with the Gomory solution, we were able to solve for all of the mainland states of the US. Do you remember that at all? Okay. And I told you that basically the difference between the two is not really in the, is not even in the solver, even though the solvers are different. The difference that we had there was in the formulation, right? We had a callback. We, like back then we called it a callback, or like lazy way to add constraints that eliminate subtours. So we had tour and eliminators, like a pool of tour and eliminating constraints that each of them would be able to eliminate a single tour, but there was an exponential number of those constraints. And what we ended up doing is we ended up to write down a program that was getting a feasible like assignment, or like a collection of subtours. Just as a reminder, we had, let's say that you have this this graph, and this is your this is when you're solving an LP relaxation. It's just a reminder. You might end up, instead of having a single tour across the entire graph in the TSP problem. Do you remember TSP problem? Okay. So instead of having a single tour, it might get split into several subtours. And we have written down a piece of code that was giving us a linear inequality that that is eliminating a solution that is corresponding to this specific division into subtours. Do you remember that? Okay. You don't remember that? Vaguely. Okay. Let me actually come back to. Actually, I have that in this set of slides, because I feel like this is something that is very important at this point. Yeah. So we had a traveling salesman problem, and it was like the first incomplete formulation that we have come up with was with it basically constrained. It consisted of 2 constraints, and then we ended up saying that it looks like an assignment problem. It was in fact an assignment problem, and then we realized that it just means that a tour can be split a thing like this would be a feasible solution for this original formulation, and this is not something that we want, and therefore we have come up with 2 kind of ways to eliminate subtours, and basically each of these ways had an exponential number of inequalities. So here we had an inequality for each subset of n nodes, and here we also had an inequality for each subset of nodes that is like has a cardinality greater than 2 and less than n minus 1. And how we constructed, for example, this cut set constraints, we had an understanding that a salesperson must leave at least once from each group of cities. And so we were like, for example, here we would take this group of cities F, and for this group of cities we would say, okay, a salesperson has to leave this group of cities. So let's add to our formulation a constraint that corresponds to S being 1, 2, 3, the set of nodes 1, 2, 3, and add that into the original formulation, and that would make sure that we never again see this solution as our optimal solution to the problem, because it becomes infeasible of our LP problem. And basically what I'm talking about right now is following the exact same kind of logic. Oh, sorry, skip through. Yeah, here our set F is that set of all eliminating constraints, subtotal eliminating constraints, and we are able to pick from this set and add to our problem iteratively, and therefore we don't have to add all of them, and we can basically the majority of this subtotal eliminating constraints are not going to be added ever. Okay. But this approach with subtotal eliminating constraints is just one example of it, and it only works with for traveling salesman person problem. There is a way to do that, and like in the more general case, it's called the Gomory's fractional cutting plane algorithm, and I think I will introduce it this time, and probably I will give more examples next time. But basically, it's a more general kind of approach to a cutting plane algorithm that can be used for any integer programming problem. So let's consider the problem of maximization of x being an integral vector of the cx such that ax is equal to b, x greater than or equal than 0. So it's the standard form of this inequalities. Solution of a linear programming relaxation results in a vector x that we're going to be calling xlp. And a separation of the set of variables into two subgroups. One is called the basic variables, and the other group is called non-basic variables. Such that basic variables and non-basic variables is a separation of the entire set of variables, and also they do not have anything in the intersection. So it's indeed a partition. And once we have solved this this linear programming relaxation, we can write down an equivalent reformulation of this original problem. It can be written this way. So this is kind of obvious. It should be obvious for those who know like linear programming and what like basic non-basic variables are. But long story short, you can always come up with a solution of an LP such that part of this of the variables are equal to 0, and then the other part is not equal to 0, right? And those are called basic and non-basic variables. And this leads us to basically like a set of an equivalent. Okay, not going very far into details. I just have to say that these variables over here are allowed to be basically they are at the optimal solution. These variables over here are going to be equal to 0, and these variables over here are not going to be equal to 0, which is the separation between basic and non-basic variables. But generally speaking, we can come up with the coefficients a bar and the coefficients of the objective value, so that basically this this expression over here is the exact equivalent reformulation of the original problem, and all of these coefficients, for example, over here, are negative. So, or like not they are non-positive. Therefore, it doesn't really make any sense to set this this variables xj to be greater than to be greater than 0. If the basic optimal solution XLP is not integral, then there is a component U that is a basic component, such that the AU0 bar is not an integer value, doesn't have an integer value. How do we know that? Anyone can tell me how we do know that? Why is that the case? So we are looking at this equation right here, because it's talking about a bars, and they are only defined over here. And here we see that non-basic variables. So that there exists an optimal solution in which all of the non-basic variables are equal to 0, right? And therefore, this entire part at the optimal solution is going to be equal to 0. And then we know that xu is a non-integral value, takes a non-integral value at this point, at this optimal point. And since xu is equal to a u0 bar, then a u0 bar also has to be a non-integral value. Okay. And so the CG cut in this case is gonna be this cut over here, which is basically applying the third CG inequality to an inequality that that arises from this equation, right? So we are taking we are basically saying that xu plus the summation over all of the non-basic variables plus xj must be less than or equal than a u0, just because. So okay, should I write it down? Let me know if this is obvious from this equation, because we actually never were talking about using the CG inequality from the equation. Yeah. So the equation is telling us that xu plus summation of over g in mb a G0 or and uj bar xj is equal to a bar u0. This is the equation, right? Corresponding to the u basic component. If we get to round down this numbers over here, we will get xu plus summation j in and b a bar the flooring of a bar uj times xj less or equal than a bar u0, just because this xj bar is greater than or equal than 0. From this equation, we get to this inequality because we have reduced this part. Then we just say that this part on the left is always integral, and the right hand side is not integral. Therefore, xu plus it wouldn't change anything if we were to just for this right hand side just by the same argumentation as we had when we were proving the third CG inequality. Is that not clear? Okay. J in and B a bar uj at j as an equal than flooring of a u0. I would like to repeat whatever is not clear at this point, because I feel like it's an important part, and it's quite simple to understand. Do you want me to repeat anything? Do you have any questions? No? Okay. So now we have a proposition that is saying, so from this cut, from this inequality, we would like to prove the following inequality to be a cut. So this thing we already know that it is a cut. Why is this a cut? So for cut, it's not enough to be just a valid inequality. It also needs to be kind of separating xu, and we know like it needs to separate xlp from the the xlp has to be not satisfied by this inequality. This the xlp that has to not satisfy this inequality because it's a cut. Why is that the case? Yeah, absolutely. But in this particular case, why like how do we prove that this? So far, these three things have proven that this inequality is in fact a valid inequality.
So
Right. Yeah.
And xu is a fraction. So xu is equal to a times b. So we round down into
It's going to be absolutely, yeah, exactly, yeah, that's right. So from now from the fact that this thing is cut, we need to show that this thing is cut. So it's this kind of a separate kind of proposition. For u being a basic coefficient, define the following fu fu0 to be this thing over here, and fuj to be this thing over here for j in nb. So it's basically, so this thing over here is fu0, and this thing over here is it's the other way around. It's fuj, and this is fu0. The CG inequality that we are trying to prove right now is can be written this way. Now we just need to observe that 0 is less than or equal than fuj is less than 1, strictly less, because well, because of the properties of rounding, and 0 is less than fu, like strictly less than fu0 is less than 1. Why is this less? Why is it not less than or equal? So it's specifically for this u. Yeah. Well, it's because we have assumed that a u bar is a fractional number. Like we have shown that it's like there is one. And therefore we did like we do have some like misalignment between these two numbers, and therefore xjlp is equal to and we know that xjlp is equal to 0 for j in non-basic variables, and therefore when we substitute this into this inequality, we would get out therefore the summation over the non-basic variables fuj xjlp is equal to 0, and that is less than fu0, right? Because fu0 is strictly greater than 0 just by our observation. And now we just so basically left hand side is equal to 0 at the point, and the right hand side is greater than 0, and therefore this inequality does not hold at the xlp. Therefore this inequality is not satisfied by xlp itself. And now we just need to show that this inequality is satisfied by all other points from the set, from the feasible set. And for that, we just need to observe that xu is equal to this thing over here. And if we substitute this thing over here into this inequality, instead of xu, we will get this inequality. Therefore, it's a valid inequality on one hand, and on the other hand, it's a cut. Okay. The slack s is a non-negative integer variable because basically it's equal to this thing, and this thing over here is okay, so it's it should be the other way around, I believe, because it's minus fu0. But anyway, so the thing is the slack s is a non-negative integer variable which we can exploit later in the algorithm that we are trying to build. We are gonna like in the algorithm of like an example of which I will give you later. So at this point we have found out that essentially this way we can always construct valid cuts, or like about like basically we can always for any optimal solution of for any LP relaxation, we can and it's like basic solution, we can construct a cut like in a systematic way, in an algorithmic way. That would be a valid cut, and therefore and we can like basically we can add these cuts back to this to the formulation and make it an iterative algorithm, and at which at some point like it should be terminating. It needs to be proven that it will take a finite number of steps, but it's like in practice it is an extremely efficient algorithm. And the next time we will I will repeat this last part about the slack, and I will also give you an example of this Gomory algorithm, and we will consider the Bander's algorithm as well, which is applied to not only integer programming problems, but also mixed integer programming problems. For now, we are done. Thank you very much. See you tomorrow.